Today's lesson is similar to the last one because in the last lesson we talked about the force that caused charged particles to attract or repel. Well, why are there forces involved in the first place? Because there's a field. Remember we talked about it being a field force? So the gravitational force is a field force because there's a distance between you and the particle that's causing gravity to affect it. Or there's a distance between two charged particles, so it's a field force. So just like there's a gravitational field all around you, and you don't even realize it, but the gravitational field around you is a bunch of, imagine like an infinite amount of arrows pointing down. That's what the gravitational field is around you right now. That's how you visualize this in math. Because which way is gravity pulling you? Down. So when we work on electric fields now, what we're going to have to recognize is that positive and negative particles distort the field around them differently. And those arrows for gravity that we just point down with are no longer going to only point down, but maybe left to right, or they're going to interact between the two particles themselves. I'm going to use the word source a lot. I'm going to use the word source. And source just means a charged particle that is much greater in magnitude of charge than anything nearby. For example, if you had a sphere with a charge of like 35 coulombs versus a single proton, this is much greater, on the order of like times 10 to the 20 greater than the single proton that's nearby. So the source would be the charged sphere, and the proton would be what we call like the test charge or the extra charge. So when we're looking at this lesson today, we're not really looking at like two small charged particles anymore. We're looking at what if we have a source of electric force or electric field in this case that provides some pull or push to other particles around it. Kind of like, what's the source of gravitational pull for us? What's the source that provides gravity for us? The Earth itself. Why is the Earth the source? Because it has the most what? Mass. So like the Earth has the most mass compared to the objects relative to it or around it, an electric charge with a great value would be considered the electric source. All right? So let's go on to take a look at this first slide. So this is what I'm referring to. So look at the larger, now they look larger in size, but just look at the number of charges. So Q on the right side that's blue, and Q on the left side that's red here, the positive and the negative, those are my sources. So if I have, in this case, if I have a positive source, I could think of that as, well, if I bring a proton near it, what's going to happen with positive? It's going to repel, so the arrow for the field is drawn to the right. Then if I look at a negative source, in blue here, if I take a look at a negative source, what I'll see is if I bring a proton near it, proton is going to be like what's called our test charge. If I bring a proton near it, this proton will get pulled toward the source. So the field is drawn toward a negative source. So we're going to see in this section that we always think about our sources as if, what would they do to a positive charge? So you introduce this positive charge, we call it a test charge. Okay, test charge at the top there. You bring a test charge nearby, what would happen? If it would get pushed away, you draw the field lines away. If it would get pulled toward, you draw the field lines toward. Whereas with gravity, like I was saying a moment ago, the field lines for gravity around you are all drawn straight down. The field lines for gravity are drawn straight down because the center of the Earth for us is straight down from where we're standing. So our formula in this section, you can go take a look at, and I want to point some stuff out in this formula. Let's first start right here, and let's take a look at this for a little while. Anybody see anything analogous in this formula to another formula earlier in the year that we used? Anybody see anything analogous? There is a formula that looks very much like this, actually. Okay, it really does. They're different variables, but it has the same setup. E is a field. Q0 is a property of a particle. Close, very close. F equals ma, but specifically not F equals ma. Fg equals mg. So you're on the right track because that's where that does come from. So if you look at this formula and compare it, again, compare it to gravity. Now, in the last section, we compared kqq over r squared to gmm over r squared. We said those are analogous to each other. The setup is the same. Well, it is here again. Little g. What is little g? What's the value of it? Yeah, it's the acceleration due to gravitational field around you, right? Capital E is like little g. Capital E is the electric field. Capital E right here, which we're going to solve for in a minute, is the electric field itself. This capital E is like little g. It has to do with the field around you. Little g comes from the gravitational field. That's why you have acceleration. Capital E comes the electric field. Well, M. M stands for mass. This is a property of whatever the particle is, right? Well, then we look here, we see Q0. Q0 is charge. It's the charge on the actual object, on the test charge, whatever this is that's brought near it. So this is a property of the particle itself also. So this formula here is really the same as this, except instead of mass and gravity, we have charge and electric field. But still, property of the actual object in both cases, this is the field in both cases. Now, with that said, we go ahead and we solve for capital E. If we solve for capital E here, we end up getting Fe over Q0. Fe was something we knew from the last section. From section 19.2 and 19.3, Fe is really Q over R squared. But if I look at these diagrams, this Q we call the source, this Q we call the test charge. So I'm going to replace Q1 with this Q right here. Q0, or the test charge, goes here, and then these two cancel each other out. This cancels with this right here. So it turns out that if you want to calculate the electric field produced by a source, all you need is the source itself and how far away your test charge is. Again, Kc is a constant. All you need is the source itself, Q, over the distance away from the source that you're testing. So if I had, it's not easy to do this because to produce this much electric charge on a given small spherical body would end up most likely electrocuting and shocking somewhere. So if I had a sphere of test charge and I used that apparatus the other day, I'm not actually going to take that. It's all box there. I had a charge sensor the other day that Anthony was using to test the charge inside of the Faraday's pail. Remember we had that little pail there and he was rubbing things together and it showed the charge on the screen? Well, what happened here is if you have a source of electric charge and you bring the sensor closer to it, the field is going to get stronger. So that's what's happening here. Look at the denominator. It's again over R squared, right? When something is over R squared, that means that it's indirectly related to the distance. So if I get closer to the source, it's actually getting stronger because I'm decreasing R, I'd be increasing capital E. They're indirectly related again. So what's happening, I want you to think about is this. Imagine this like the Earth. If you're further from the Earth, gravity goes down. If you're closer, gravity goes up. It's very, very similar, but now we're looking at the actual electric field. Okay, this is like as if we were doing this. Imagine if I was calculating little g, and I tell you, well, in this class we've said it's 9.81, but I also mentioned to you, as you get higher in elevation, gravity goes down. Well, little g is a function of R squared indirectly. As you get further from the center of the Earth, that value is also going to go down. So little g, although we didn't really calculate it, we just experimentally determined it with the picket fence and other stuff. With the pendulum, you calculated g with that experiment. Well, here, if you actually wanted to figure out the value of g, it would also be indirectly related to R squared. And that makes sense, because as you get further in elevation above the Earth, gravity goes down. You feel less weight. As you get closer to the center of the Earth, gravity goes up. So this capital E, again, is like calculating little g here. All right? Here's our formula we're going to most likely use. But you also should be familiar with this formula over here on the other end. Okay? Check your formula sheet. I know I give you the one in the blue box on the far right. I don't know if I give you this formula. I do? Okay. So you have both of them. So if you need to calculate the electric force, if you're given the field presence, and you're given whatever the test charge is, you just multiply those two to get the actual force. Or you can use this formula for the electric force from the last section if you have two charged particles instead. Okay, depends on what you're given. Depends on what you're given. And look at the units, please, last but not least. Look at the units. The units for electric field were newtons. The unit for charge were coulombs. The units for the electric force were newtons. The unit for charge is coulombs. This is newtons per coulomb. Because it's really, if you look at this, what's the units for this? This is a newton right here. Remember, this came from Fe from the last section. This is a Newton in the numerator, and the denominator is a Coulomb. So it's newtons over coulombs. That's where the units come from for electric field. It's like a rating, okay? It's saying, you know what? If you're in the presence of my electric field, you're going to feel this many newtons for every coulomb that you're worth. Newtons per coulomb. Newtons per coulomb. That's what a rating is, okay? It's a rating value. Let's talk about field lines. This is what we were mentioning a moment ago. What you need to think about is if I take by the way, this is just something that's been accepted over time for science. Scientists a long time ago thought, let's be consistent with the way we're talking about fields. So let's always think about, what if we bring a proton in the presence of a field? What would happen to it? That's the question that's always asked. Why didn't they say electron? I honestly don't know. A long time ago, someone way smarter than me that really came up with a lot of this kind of stuff said, hey, you know what? We're going to universally say that when we want to determine electric fields, think about a proton. Because if one scientist in the U.S. thinks about protons and another in another country thinks about electrons, we start getting into issues with like, all right, your fields are drawn one way, mine are drawn the other way. Now we have to figure out what charge were you talking about. So to universally accept this, kind of like what we should do with units, right? Remember I talk about this? We should really not be using feet and yards and miles. They don't make sense at all. We should all be using meters and kilometers. It makes so much more sense because the prefixes actually work out. The American system that was adopted from England, the English units, don't make any sense. Honestly, it has to do with being stubborn and being set in ways. People don't want to change their ways, so we have never changed it. But this is universally accepted, that all you do is think about a proton. I put a proton here. Positive, positive. What's going to happen? It's going to push away, so which way are the field line's drawn? Away. Okay, this source will cause any objects to get pushed away from it. Whereas on the right side, a negative source here, if I take a positive charge, I take a proton, and I bring a little proton out here, which way is that proton going to want to move? Toward the negative. They are attractive. So the field lines are drawn in a way such that it demonstrates how a proton would move. Okay? The field lines are drawn demonstrating how a proton in the presence of that field would itself move. All right, so let's take a look at some general rules for field lines. So this is all really theoretical stuff right now. We'll do a mathematical example in a minute. So field lines first, we say that they can begin on a positive charge or at infinity and must end at a negative charge or at infinity. So let's think about that for those last two examples again. So for the positive source, we drew lines like this. All right, so look at this. Where are the lines beginning? They're beginning on the positive source. That's right here. So they can begin on a positive charge. And where are they ending in this case? They must end, in this case, at infinity. So that's what we're looking at for a positive source. Yeah? A what? An infinite charge? Like a positive source that's so great? No, because charge is conserved. Remember we talked about conservation of charge in the galaxy and the universe? So if I lose some electrons, something has to gain them. So an infinite amount would mean that you're getting them from nowhere, right? You're creating your own charge. When in reality, it's a transfer of charge always. So, good question. Hey, for the second part, for the negative charge, we have to say to ourselves, well, look at the other part. It says field lines can begin at infinity. That's what's happening here. Because think about it. Where are these field lines being drawn from? Out here. And they're ending at the negative charge. So they must end at the negative charge. So either way, they could start at the positive and go to infinity, or start at infinity out here, a distance away at infinity, and come toward the negative charge. That's all the first one is saying. Okay, it's giving you the directions of the field lines. The second one says the number of field lines is proportional to the magnitude. What does that mean? The number of field lines is proportional to the magnitude of the charge.
The bigger the charge, the more lines.
Exactly. The greater the charge, the more lines you have. Now, it's not like if I add one more line, right, to this field, it means that you go up by like 1 coulomb. There's no number that's set. It's a more relative statement. So for example, if I wanted to show that the negative charge was double the positive source, I would put double the amount of arrows. So if the positive source was like 3 coulombs, the negative would be negative 6 coulombs. The more lines drawn in the diagram, it means the stronger the source is. Again, the more lines drawn, the stronger the source. So if I have double the lines in 2 figures, I know that one of these is double the strength of the other. So this source that's negative is twice as strong as the positive because there's twice as many arrows. It's a general way to show lines. You're going to see this if you end up taking anything in engineering or calculus. You see what are called field lines. And these are field lines being drawn in, but usually they're vector field lines. But the more lines, the stronger the field. So this is a stronger field. Forget negative or positive for a minute, even if they're both positive. More lines, stronger field. And more lines, stronger field. It's a relative statement. There's no number to it at all. And then field lines in the same field cannot cross. All that means is that I can't draw a field line that does this. Okay, those lines cannot have. Can't have lines that I'm crossing. All right, let's take a look at some sample fields just to give you an idea of what I'm referring to. So let's start with the first one here. Start with this first one. So in the first diagram, we're seeing a positive source and a negative source near one another. And we were told a minute ago that our field lines have to start at a positive and end at infinity. Or start at infinity and end at a negative. Well, take a look at what's happening here. The field itself starts at the positive charge, and the field lines are drawn away, going toward infinity. So they start at a positive and end at infinity, all over here. Part of the field, though, connects to the negative source, and we can see that it starts at a positive and ends at the negative. Or it starts out here at infinity and ends at the negative. So the concept here is that field lines are drawn really from the positive to the negative source. This is going to be analogous to what we're going to see later in the year with heat transfer. Heat always moves from hot to cold. It never works the other way around. It's physically impossible. Heat, if there's a part of the room that's hotter than the others, the heat will move from that part to you, not from you to the actual part. So usually what you see is that you have what's called like forced convection in certain heating systems. Based on the density, you have air conditioners at the top of the room, and you have heating systems at the bottom of the room. George, you're just stretching, or do you have a hand up? Let's look at the second one to compare the difference here. So let's look at both at the same time, actually, so you can see the difference. So in the second diagram, instead of having a positive and a negative source, you have 2 positive sources. So what are they going to do? Positive near positive. What do they do to each other? They push away. They repel. So look at the field lines. The field lines are showing that. The field lines are saying, like, you know what? My electric field wants to go out. It always wants to go out from a positive. But these two are not going to hit each other because they're going to repel. So this middle here is almost like a barrier. How many of you've all done, I shouldn't even say how many of you. When you were a child, you played with magnets. You did it at some point in your life, whether you remember it or not. When you brought 2 north poles together, what happened? You felt that repulsion, right? That's literally this. This is how you would visualize it. Okay, this is electric sources, so it's a little bit different than a magnetic source, but it's analogous in nature to 2 north poles getting tried to push together. You physically can't do it, right? Isn't it annoying? You're like pushing it, and it pushes you back apart. That's what you're seeing. You're seeing field lines that are almost like arguing with one another, saying, you know, I can't get in close to you. I'm going to push away. So that field line is like a barrier. It's like having a barrier right down the middle here, saying, yeah, you know what? They're never going to cross that barrier, those field lines. The last one is just to show you the idea of 2 different sources that are magnitude of differences. So you've got a positive and negative. That was the same as the first diagram, right? This was pretty much the first diagram, except now the positive source is twice as strong as the negative source. So all you're going to see here, is the number of field lines change. Take a look at the field lines. Count how many there are on the positive source. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Go to the negative side. 1, 2, 3, 4, 5, 6, 7, 8. It's not a coincidence that there are double the amount of field lines on the left. Well, this source was twice as strong as the one on the far right. So for example, For example, I could have a positive source of 7 coulombs and a negative source of negative 3.5 coulombs, and that would be this diagram right here. I'm not going to redraw all those field lines right now because they're literally in front of you. But this is an example numerically of what I'm referring to. You have a positive source of 7 coulombs. You have a negative of negative 3.5 coulombs. This is double the strength. Forget the sign. Just look at the magnitude. What does magnitude mean again? What does magnitude mean? There's a simple way to think about magnitude.
Amount of the including direction, I guess.
So what do we call that in math?
The absolute value.
Absolute value. So look at the absolute value of these numbers. This one is clearly double this one, right? 7 is double 3.5. We should know that number by now. So it's double the value in magnitude, but not necessarily in charge. The charge doesn't really matter as much. It's the magnitude that we're really referring to here. Yes?
I just forgot. What's the for the negative forces? Where does the field start from? Where does the field line start from?
So, if we think about how field lines are drawn, they're drawn in a way to show the way a proton would move. Would a proton go toward a negative source or away from it? So the field lines are drawn toward the negative source. Okay? And they're shown away from positives. You could say, Ernest, that they start at infinity, meaning the field lines start out here at some distance really far away and are drawn toward that source. Because even if there's a proton as far away as this, it still feels a little bit of a pull. Is that pull significant? No. It's like the equivalent of saying, if you're far enough from the Earth or from the sun, you're like an asteroid in another galaxy, you do feel the pull from the sun, but it's pretty much zero because you're so far away. But you could start at an infinite distance away, really. Let's jump into some math now. All I've got for you today are 2 math questions to finish on here. So that was mainly our theoretical portion. Let's jump right into this now. So a charge of 10 microcoulombs produces an electric field. So that's your what? What's the word for that again? It produces the field. We call that a source. Thank you. Good. Please, let's write that down right away, guys. Produces an electric field. This is synonymous for the word source. So Q of 10 microcoulombs is the source. Determine the electric field at a point 10 centimeters from this charge, from the source. Then determine the electric force felt by an electron at this distance. Will the force be attractive or repulsive? So this is a 3-part problem. You've got parts A, B, and C, not written that way, but it's a 3-parter. So the first part says, determine the electric field 10 centimeters from the charge. Now, I have options. I could start with this formula, or I could start with this formula. Both of these can be solved for electric field because they both have capital E in them. So for the first part of this question, it says again, determine the electric field. Right here, I'm underlining in red. Okay, see what's underlined in red there? That part is the first part of the problem. So we're trying to figure out, I hate this eraser on this thing, I really hate it. We're trying to figure out capital E in this problem for the first part. So do I use the first or the second formula? Do I use the first formula on the left or the second formula on the right? What do you think?
First one on the right.
Why?
Well, we're looking for capital E.
Oh, it's in the other one also, though.
Yeah, but it's easier because of the way it's formatted.
I agree, but there's actually a better reason than that. It is easier because it's already solved for E over here. Go ahead, keep going, Ernest.
It gives you the distance.
And what else does it give you?
And the charge with Q.
So what do you have? You've got this and this, right? And you got K, it's a constant. So you have everything in this formula right here. So you absolutely will use this formula to calculate capital E. Because again, you're given the source, 10 times 10 to the negative 6, right? Micro, 10 to the negative 6. You're given the source, you're given the distance away, 10 centimeters or 0.1 meter. So because you're given those 2 values, the source and the distance away, you will use the first formula. Remember, Q0 over here, take a look up please. Q0 on the right side is whatever the test charge is. We're going to use that in a little because we're going to look at the electron in a minute. And the electron is going to be used here in a moment. Okay, but Q0 is not the source. Q in the formula on the left is the source. Q0 is the test charge. Whatever charged particle is brought in the proximity or brought near the proximity of the source. So remember, the source is like the Earth. You yourself are like Q0. When you're near the Earth, what happens to you? You get pulled to the Earth, right? You're Q0. You're the test charge. The Earth is capital E. It's like the source. It's Q, the source. It produces a field, capital E. This is very analogous to gravity. So I try to make allusions, or I try to make correlations, connections, thank you, between the two, because it's easier, I think, for you guys to visualize gravity than it is to visualize an electric source. So let's use that first formula. We'll get to the other parts in a minute. I'm going to plug right into the first formula. Okay, I've got my numbers plugged in. This is K, it's a constant. This is the source. Ignore this little line here. I don't know why it's there. Just like my wrist is like us leaning on this. Ignore those. So 9 times 10 to the 9 times 10 times 10 to the negative 6 all over 0.1 squared. Again, why is it 10 to the negative 6? Micro. Look at the units in the original part. It was given as microcoulombs. It was given as microcoulombs. I know my units are going to be newtons per coulomb because it's an electric field. So I can jot that down already because everything's in standard units. What do I get as a number for this? What do you got? 9 million? All right, so I have 9 times 10 to the 6, which is million. 9 million newtons per coulomb. A lot of your answers in this section are going to be in terms of science or in scientific notation. Okay? So that's the electric field present at that distance. So again, let's visualize, please, everybody, together. Here's the source. A tenth of a meter is 10 centimeters. So here's the location we're looking at. Source, location right here. Now, at this location where my hand is, okay, my hand is the location, my fist is the source. At this location, you will feel an electric field strength of 9 times 10 to the 6 if you are a simple proton. Now, since this is a positive source, which way would the proton move? Positive source. Was it positive? Yeah, it was positive source. Since it's a positive source, which way would the proton want to move? Away, because they have what force? Positive. But what is it? Repulsion, right? Repulsion. If it were a negative, it would want to move toward it. What are we going to look at now? It says, then determine the electric force felt by an electron, which is negative, right? And then the follow-up says, will it be attractive or repulsive? You know it's going to be attractive because you have a positive source, an electron out here. They're going to naturally pull together. So as a result, we have to figure out, though, what is that force? It says determine the electric force. So I could do two things. I could say to myself, you know what? Let me go back to this formula. I could do this from last section. Honestly, that's fine. You can do that. If you want to use that route, that's fine, but that's the long route. That's the long route. Because look, ready? What goes in for KC? Come on, people. This should be like instant. Let's go. Thank you. Look up. Too many are doing other crap. Look up. Q1 is the actual charge on the first particle. That's your source. Q2, the other particle. That's the electron. R, 0.1 squared. The same numbers we just used. Well, we already took into account KQ over R squared. We already did this part of the formula. KQ1, R squared. That's this right here. We calculated E already. So this right here is like capital E. All we have to do is multiply it by Q2. So really, we're going to use this formula at the top. Again, this right here is really capital E. Look at the formula for capital E we just used. It's the same thing. The beginning part of the force formula from last section, that is capital E. These are the same things. So we already calculated capital E. Why would we plug all these back in again? It's more work, right? So just take whatever this answer is in the circle here in blue, that's capital E, and multiply it by whatever the other charge is. Well, that's the charge of an electron. So whether you call it Q2 or Q0, the electron charge is going to go in that place. So again, I'm going to use this formula because it's easier. It makes more sense that we already calculated capital E. What's the charge on an electron? If you don't memorize it, that's not a big deal, but it's in your last note. You remember it?
So it's 1 times 10 to the negative 16.
Really close. You got to put them together.
1.6 times 10 to the negative 19.
You put the 6 in with the other one, yeah. It's negative 1, it's an electron. So negative 1.6 times 10 to the negative 19. Now, units, newtons per coulomb. Units, coulomb. What are my units? My answer going to be if I have newtons per coulomb times coulomb. Am I?
Would it be newtons over coulomb squared?
Close, but the coulomb here is in the numerator, mine.
Oh, so newtons. So it cancel out.
Good, so it's just?
Just newtons.
Very good. And what are we calculating?
Oh, yeah,
Force is measured in? You see how it's always going to make sense, the numbers and the units, because you have things that cancel. Coulombs cancel, leaving newtons. Newtons are force. You're calculating a force. So all we do is multiply these two values together. I'm going to get negative 1.44 times 10 to the negative 12 newtons. Again, it's only negative because you got a positive source, a negative electron. Positive times negative gives you negative. All this means, remember, for a two-particle system, we're not looking at a three-particle system right now. For a two-particle system, a negative force simply means they're attractive. For an electrical two-particle system, a negative answer means they're attractive. How do you know physically? Positive, negative, attract. Positive, negative, attract. Okay? We're always going to attract. Ernest.
What if it's just says negative 1 and negative 12? Oh, wait, I see.
Yeah, you see what you did? You used K instead of E.
Yeah.
You put K here instead of E. So to summarize, right? We want to think about this really very much in the same way as the last section. Positive, negative, attract, positive, positive, repel, negative, negative, repel. But really in this section now we're saying, what if I look at, instead of two particles that have like small charges, one really big charge, what's going to happen as a result? That's capital E. The one big charge is what gave us the electric field. Now if I bring a little small charge in that field, what happens to those? That's the force we're feeling. Okay, so again, this is the field, if you want to write it down, the field due to a source. The field due to a source. This is the force felt between a source and a test charge. This is the field due to a source. This is the force felt due to a field with a test charge in that field. Lauren.
The aircraft was a which one is which?
Oh, sorry. So 9 times 10 to the 6 is a field due to a source. Due to a source. The number at the bottom in newtons is the force felt on a test charge because of the source. So what you'll notice about a field is that a field is only a function of the source itself. Right? Look at the formula for E. The formula for E was K, Q over R squared. All that mattered for E was the source itself. That's what provided the field. Just like what provides gravity again? The Earth. The Earth is what's providing gravity. You're not doing anything. I mean, you have your own gravitational field. We talked about that earlier. But significantly, you're doing nothing. The Earth is providing gravity. The Earth is the source. This electric charge Q is the source. All right, let's look at one more example. One more example. For this example, what I want you to think about, you remember the term superposition? You better remember what that meant. I used it only once this year. Superposition. I used it with constructive and destructive interference. Constructive and destructive interference. I used the word superposition there. What did I refer to by that? Go ahead. Was it what? Not equilibrium. Lord?
Does it have to do with like charges being the same?
Not the same or the same.
So like the things being added.
Or it had to do with the summing of the amplitudes. You remember we drew two waves, and if it was constructive interference, two positive waves together made a bigger positive wave? So that's what we're really doing now. Come on, come back to me. That's what we're doing now here. We're looking at this part where we have an electric field produced by two sources. By two sources. So you've got a source on one end and a source on the other, and there's a point halfway between them. They're separated by 40 centimeters. And the question is, what's the field as a result of two sources? So what we're going to do is we're going to look at both sources individually and kind of sum them together, similar to what we did with constructive or destructive interference. So let's draw a diagram of this first. Okay, let's draw a diagram. It looks to me like we've got a positive source and we've got a negative source. The positive one is 3 times 10 to the negative 8 coulombs. The negative one is negative 2 times 10 to the negative 8 coulombs. So it might be very tempting at first to go right to the formula K Q1 Q2 over R squared. But that would give me the force felt. This asks nothing about the force felt. It says determine the electric field produced. Okay, halfway between them. So halfway between them means they're how far from each? Okay. Okay, here's the point we're looking at right here in the middle. How far away is this? This is 20 centimeters. This is 20 centimeters. Okay, not drawing a scale on this. So that point is halfway between them. I think to myself, a positive source is going to push away any positive test charges. A negative source is going to pull toward it any positive test charges. So really, if you recall, your field lines in this case are always going to be drawn like this. Yeah, they're going to come out like this also. We showed that in the diagram earlier. But this is our diagram from before. Our field lines are really being drawn toward the negative source. Okay, they're not supposed to cross. One of them crossed a little bit. Okay? So that's what's happening here. So the positive source is taking that proton. Put a proton right here, please. In your mind, put a proton here. Because of the positive source, the proton wants to move away. Because of the negative source, it also wants to the right. Because of the negative source, it also wants to move to the right. So if I get a field from this one, pushing it to the right, and I get a field from this one, pushing it to the right, what should I do to those two fields to figure out the overall field felt by this test charge in the middle? If they're both pushing it to the right, what should I probably do to them? Yeah, it just makes sense logically. If I'm pushing you to the right, and then your other friend comes over and pushes you, don't you feel the push from both people? So really here, what's happening is that one field, the positive field, is pushing things away from it, inherently since this is the middle, and push it to the right. The negative field is pulling things towards it, so it's also moving it to the right. So really we have to find both fields and add them together. We could do it separately or do it together. It doesn't matter. I'm going to do it separately to be careful to show you. So the first field, E1, this value is produced by, let's say, in this case, the positive charge. So this is going to be, again, KCQ over R squared. In this case, we'll use the positive charge first. Why am I using 0.2 for R? Why am I using 0.2 for R?
Because it was 20 centimeters of distance and 20 centimeters.
Good. The units were given in centimeters for distance of 20 centimeters. Convert that to meters. This is going to be 6750 newtons per coulomb. Now, the next part, what kind of an answer am I going to get for E2, do you think? For E2, what kind of an answer do you think I will get? What kind? Ernest? Negative. Because what's the other charge? So what's going to happen here is you're going to be very misled. Because you're going to say to yourself, oh, this is a negative source, so I'm going to get a negative field. And the negative part of the field just means it's pulling it toward it. So at the end, we're still going to add together two numbers that are considered positive because they're both to the right.
Oh.
Let me go through this real quick because it's a little bit misleading. This is something every year that confuses students. Maybe, I don't know, I got to maybe think of another way to go through this next time. Same formula, right? Now, instead of 3 times 10 to the negative 8, I'm going to use the second charge now, which is here, Q2. So I plug this in and I plug in negative 2 times 10 to the negative 8. And I'm going to get negative 4,500. But remember, the signs for electric forces and electric fields really are indicating attractive or repulsive. So when you do this next part, you think about, well, you know what? Here's the negative source over here. Here's the positive source over here. I'm in the middle. I'm being pulled both ways. Okay, well, the positive source itself pushes me this way. The negative source pulls me this way. So they're both really causing me to want to move to the right. The field is really to the right. So in reality, if I want to figure out what the overall field is, I need to add together these absolute values, and I'll write my direction at the end. 6750 plus 4,500 will give me 11,250 newtons per coulomb. Okay, again, this is the misleading part at the end. When you have two fields acting together, you need to think about the theory of what's going on in this section. Think about the theoretical part to help you with this, to remember that you're using absolute value here. So again, the field that's positive over here wants to push positive away. The field that's negative over here wants to pull negative toward it. So inherently, both of these fields are causing the middle to want to move to the right. They're causing whatever's in the middle to be pushed to the right. That's why we drew the field lines to start this problem. That's the reason in the beginning I had you draw field lines so you could see that both of these sources are causing field lines drawn to the right. So we add both of these together to get a positive to the right. Matei.
So is it always absolute value, or is that just the case when both are going in the same direction?
So if both were pushing to the left, you would put a negative in front of the absolute value for each. So yes, it's always absolute value, but if I switched, put a positive here and a negative here now, the field lines would be drawn this way, right? So you'd add two numbers together, get a number, then what would you write here? To the left, you would write. So you're using your conceptual knowledge to really answer part of the mathematical problems here. Okay? Yes?
How do you know when, like, because like at first I would have thought to draw the negative on the left and the positive on the right. So is that, like, how do you know just...
That's a great question, Ernest. I didn't even think about that. You don't. You could have drawn it the other way, and if you had drawn it the other way in your diagram, your answer would be to the left. But the magnitude would be still
The same, yeah.
11,250.
Okay.
That's a great question Ernest asked there, okay? Think about that. If I had drawn this diagram the other way around, it would be to the left. That's what Matei was asking about. But it wouldn't be right or wrong the other way. I mean, it wouldn't be wrong the other way. It would just be a different way of interpreting it. Okay? Yeah, you can think of it as negative, or you could just say to the left. You know what I mean? Because the left is negative. Take a quick 3-minute break. Okay, come right back to the lab. Maya, we're going to do the lab in another class on Monday. You come the first or second period, right? So unfortunately, they're going to be doing the lesson during the... Oh, no, they're going to do the lab first. Never mind, because we're going to do the lesson today in their class. Yep, we're good for Monday. But if you want to get a head start of the weekend, do you want it, the lab? Because it is on the computer, so it's not a hard lab. It's like a game. It has to do with the field house. So you have to like record yourself doing a diagram. I'll go over it on Monday, but if you want to get a head start, and then the questions after. Okay?